So today we start with Andreas Ioannides from Cyprus, from AII Scientific Cultural Services, and he will be talking about source localization and brain connectivity within the Gratos project. Andreas, please.
Thank you.
Go on. Thank you.
Is my screen shared right now? Do you see it?
Not yet. Yes, I think it's, yes, now we do. Yeah, now we do.
Okay.
Thank you.
Good morning, everybody. It's a great pleasure to be with you. Thank you for the invitation and to this wonderful symposium. It's a kind of first symposium for me going back to this kind of work for many, many years since coming back to Cyprus. So let me just start straight away. Okay. Let me start by a brief outline. I will start with an advertisement about 2 talks where you hear more results about ongoing work rather than what I'm going to talk about. Then I will briefly say something about universals for the inverse problems and foundation and basics based on all the results that we have and validations that we did some years ago. And then I would like to trace the history from where we are right now, because I was in a good time at the beginning of the, I think with anatomical networks were coming onto the scene, and then with the functional networks at the beginning, and then disappearing from the scene, running MEG laboratories around the world. And then I will conclude by a reminder about the 2 other talks from my team that will come in later, because they relate directly. And one of the reasons for taking this is to introduce some of the ideas for at least one of them, which, as you see, is from somebody who is not a mathematician, but somebody I think who is the kind of customer for the work that we do. So the first talk, it would be about something very basic. Christodoulos Karidevlis, who started the PhD under an IT grant with me, it would be asking some very fundamental questions which he has to pass in order to start the PhD. And namely, the first one is, can we go down to the basic physics and the raw signal and identify sources at the cortical mantle and deep in the brain just from the raw signal, directly from the raw signal for MEG and EEG? And if we can do that, can we study from the above estimates real-time linked activity between them? So without knowing anything about exactly where knowing everything about where the source is coming, but not making any tomography, can we actually say something? And then does the above analysis tell us what we expect to see? Because we know a lot about some of the systems from animal experiments and other studies. And then can this analysis tell us something new? So Christodoulos is going to cover these points because I think are essential before we go into the complicated mathematics, which often we use as a black box in order to do the results. And so this presentation could be the very last. So I thought it was very important to actually announce it here first. It would be the very last of the talk. So if you can make it, to stay in here, because I think you'll find something interesting in it. The second one is from the second presentation is from a psychiatrist. He's also doing a PhD with me, and he's not a mathematician. So I thought it was very useful for him to be exposed to this kind of environment and to do a presentation. I will try to introduce some of the results, not his results, but some of the techniques in terms of results from other topics that we have, so that there will be a connection, because you will not be describing, obviously, the mathematical part of that, but just the results and what you're aiming for. The questions that he's addressing are the following: can we use a few channel EEG, not a 200, 100 channels of EEG, and the resting data in a personalized way of delivering psychiatric services? Can we combine the descriptive reports from questionnaires from the reporting into this analysis? And this would be an attempt by psychiatrists to address these questions. Obviously, it's the first step, the beginning of this exploration, but I think it would be very interesting to actually get some outline. Now, I spent most of my time doing MEG. Why did I stay for almost 2 decades with only MEG? And the reason is this picture. You can see in this picture a number of things. In the top part, you can see the signal when you have the subject in the room, okay? And the heavy black line, do you see my cursor here? Where it says subject noise. The noise is deliberate. I never call something by subject noise. It's just an activity coming from the subject, which I might not be interested at the time. Okay, unlike the external noise, which it's always something which normally you are not interested in unless it's the stimulus that we provide to the subject. The next line is the subject signal. Is what actually comes when we add a signal to that's a single trial, okay? And what you see below is the average signal that most people used to look. Fortunately, now with some of the techniques we have, people are not doing that. And then what you see below is system noise. The key thing is that the difference that you see between the system noise, okay, and what you see in actual real signals is huge. So the dynamic range of MEG is fantastic, enormous. And that's something which is not used very much. The other thing on the right-hand side, you see what the average signal looks from a very strong somatosensory stimulation and what two single trials look. And you can see that there is a lot of variability. On the right-hand side, you see what is happening, the sensitivity is like what Piastra very nicely illustrated yesterday for a spherical case. And you see that when you use MEG and what you can actually, the signal you can get goes down to 0 for a spherical head. But as soon as you distort the system, you remove from spherical symmetry even slightly, you start seeing the depth. And that was reflected in the very nice talk that Piastra gave yesterday. And you can see different structures, okay, how similar they are. Of course, for a very superficial source, you're up here, but that's actually too much signal, okay, in some respect. I won't comment more about that. But what you see on the other side, you see things like amygdala, cerebellum, fusiform gyrus, brainstem. Those are not really deep structures. At least they are not deep structures for the way we do the analysis. Something like the thalamus is a deep structure, and that relates to what Christodoulos would be showing on Friday. So the question that Christodoulos would be addressing would be referring to this part, the very deep structures. Can we say something from the signal itself about this structure? Can we use it in a constructive way? So that's a blow-up of the previous one about the kind of signal that a source at the center of a sphere gives. In order to make use of this information, this huge dynamic range, however, you have to do everything right. And I'm glad that Gortet described everything that I want to learn. Carsten described yesterday, because having been the luxury of using MEG, I didn't need to go to conductivity. Now in Cyprus, I don't have an MEG. I have an EEG, and I want to do most of my work with few channels EEG, and I want to do it the way that Carsten is doing it. Okay, so hopefully some collaborations would be online along that. But in order to do that, you have to make everything right. In the experiments we've done in Japan, that's the system we had in Japan, we used to spend 2 or 3 hours to prepare the subject, because we were aiming at an accuracy in reconstructions of the order of 1 to 2 millimeters. And you cannot have an accuracy of 1 to 2 millimeters if you do not know where your sensors are to that accuracy. So in order to do that, you have to go through a lot of steps, even correcting for the distortions you see on the bottom left part side that you put when you put the pohemus, for example, to get the 2 coils on the part. So if you want to get accuracy at that level, you have to do the experiment at that level, and this is something which is not always happening. I'm not going to talk anything about magnetic field tomography, the techniques developed back in 1989. This is the method we use throughout. It has advantages, theoretical and practical, which if there is an opportunity next year, I would love to talk just about that, because we are actually working, trying to make it part of a open access software. And it allows us, by doing separate calculations, which is historical, you see why later on, from 4 different sides of the head, looking at the other side too, but only in order to allow for the activity that's coming in, and then combining everything together into a unified source space that can look at the whole of the brain millisecond by millisecond with an accuracy which is really exceptional, as many people now are finding with MEG. Now, I'm not going to talk about the method. I'm not going to talk about the results from this method, except to show you a couple of examples. I spent 12 years in Japan, and I wanted to address a few questions in those days, and I'll come to the 2 questions later. The third question was that how accurately can MEG localize? The only way to do that is to have a gold standard. And for the first years of my career in MEG, I really had no gold standard. People were asking me, what is the accuracy of MEG? And I would say it's better than 1 centimeter, but I couldn't say anything more. I could say more only with the work that you've done with Keiji Tanaka and the late Kank, who was the head of the MRI group, because they could do MRI at a better accuracy than what we wanted. We could reproduce the ocular dominus columns from the same subject in 2 different days and get the same results. That meant that they have a sub-millimeter spatial resolution. So what we did 3 fMRI experiments and 2 MEG experiments in order to have the same subject, seeing the same stimuli, and then done the analysis using exactly the same parameters for the stimulus, but of course adjusting the analysis for what the MEG and fMRI can look. And what you see on the image, you see the fMRI in blue, and you see the MEG at p0.05 statistical significance at a given time slice, looking at single trial reconstructions and doing the statistics on top of that. And with an accuracy of p0.001, so it's raising the threshold to that with the red circle. When I first saw this picture, I thought I was seeing an error that something from the fMRI was copied into the MEG results, but no, it wasn't. But in order to get to these results, we have to correct something from fMRI, the distortions that you have with the 4 Tesla machine, which they didn't know because they were fitting the ocular dominus columns on the distorted anatomical images they obtain with the same scanner. So you have to obtain, because what we have with MEG, we are looking at absolute space. The question we wanted to address after that was whether or not we can actually localize deep sources. But we couldn't do that. We couldn't do shimming and other things that needed to do in the fMRI. So we use eye movement examples in order to do that. And we looked at the activity from the brainstem, and we found exactly the ipsilateral activation for movements to the left and the right. What you see on the left side here, on the left brainstem, we see the activation on the right side for the stimulus to the right, and more central and widespread for up and down movements. So we knew we had the resolution that we claimed. I avoided looking at deep sources because we did not have the gold standard validation, but nowadays everybody seems to be doing it, even though without doing validation. But I still insist that somebody has to do a proper fMRI MEG experiment with validation. Now, for a didactic purpose, I want you how I got into this part. When I started with MEG, I could hear a lot of physicists, very good physicists, talking about biology with clearly not having a clue about what it was, and a lot of biologists talking about physics as if they knew everything about physics. For the first time, I heard somebody who was a psychiatrist, who was interested in physics, knew that he knew a little about physics, which made some really insightful comments. What he said up in 1986, I think, at the time, was that if you want to make MEG relevant, then you have to look at deep sources. You can avoid that. And you have to do it with an instrument that is actually comfortable for clinical applications. And at the end of the talk, I saw him and I said to him, look, I believe I will have what you want in about 6 months' time. He looked at me kind of strangely and said, okay, when you do it, come and see me. 3 months later, I went to his office with some images, and that was the beginning of a very strong friendship that lasted the test of time. We were still very friendly, much shorter than what we were at that time, and a wonderful adventure in science, which I want to share with you. At that time, we had no software like the one. We have to invent everything for ourselves. And what you see on the left, you see what we call a depth plot, in which we show the activity, just the intensity of the current density modulus, as a function of depth and as a function of time for a go-no-go experiment, a CMP symmetric avoidance experiment, which I will describe in a minute. And what you see on the right, you see the tomographic images, which took 2 weeks to make one image of one slice. Okay, so one image, one time slice. And what you see on the right is the results when you have the transputer, and we actually, it was a supercomputer at the time, ran the whole activation throughout the source space over time. To begin with, what I wanted to do first is to see whether or not what leakage there is around. And here you can see a picture from the same experiment. It was a nodular experiment. You have tones that tell you whether to move or not, or or not to move 3.5 seconds later. And you can see the activation in the auditory cortex, about 100 milliseconds, and you see what leakage there is around. And on the right, you see some of the first examples of activation curves, namely putting a region of interest where you see activity and then tracking over time how this activity looks like. And what you can see on the left, you can see how much leakage there is over space on the top left, and you can see over time how the activation, how strong it is relative to the background. I won't describe any of the results. That's not the point of the exercise. The point of the exercise is to show what kind of results we can get. But around that time, Young published his results using the Van Ensen data for connectivity. And when I saw this picture, I was really excited. I went back to my team. We had the 2 PhD students and the programmer, and I said to them, look, this is important. We can do this, and we can show how things move in the brain in exactly this way. I was also at the Open University in the UK, and I was doing a course on graph theory. And I said, this is it. That's what the future looks like. So I wanted the 2 PhD students to consider abandoning their PhD and going into this one, but none of them wanted to. And me and my programmer, who was extremely competent, didn't want to shift. So that's how it stayed. But we tried to do connectivity by doing it this way. So you have the activation every 10 milliseconds in this case. It was a CMV experiment. So we took the activity and we have a window of something like 50 milliseconds that we sum the activity, the modulus of the current density, and we look at connections between areas, how the activity moves. You can say that this in 1994 was the first results from MEG showing activation moving from one place to another. It's only of historical value, of course, compared to others. But this is something else. This was from some animations I did by looking at slices together, which clearly show frontoparietal alpha rhythm activity going in the time between the warning stimulus, the stimulus that tells the subject whether he has to move or not, and the 3 seconds later, 3.5 seconds later, a stimulus that is going to tell him either make the movement or not, or that he knows that he doesn't have to make a movement. That memory trace seems to be held in the brain by these interactions between anterior cingulate kind of area and the parietal areas. Now, what is still missing from this analysis? When I was doing that, I knew that something was missing. The elements that Peter Phoenix has identified were there. We could identify the structures in the picture, but we could not really say something about the deep structures with certainty because of we did not have any way to be sure about the localization accuracy of our method. Remember, that was 1993. The fMRI MEG experiments got done 10 years later. So we knew that it was like, my analogy is that the pictures that we had at that time, it was like looking at a beautiful painting in which, say, a rose bush, and you see only the flowers and the leaves. It's beautiful, but something is missing. The trunk that keeps everything together is missing. A static picture is incomplete without an understanding of the dynamics that makes from buds to roses. So you need, in order to do that, you can't do that. And you can, if we go back to this picture, you can see why. In all the experiments we did, we focus on this activation here around V1 and the neighboring areas, because that's the only thing we could sample with the kind of experiments we did. There was no resting state analysis at that time. But we pushed ahead. So that's an example from experience we've done with the MEG laboratory I was running in Jülich with the late Markus Streit, in which you look at the difference between activation, doing the network analysis with time-delayed mutual information between the areas that we could sample, focusing only at the cortex and looking at activity. And when I say cortex, I even include amygdala. For us, this is not deep. When I say deep, I mean things like the thalamus and brainstem. So we found out that the difference between controls and schizophrenic patients could be summarized not by where the activity was. That was a complicated story that we understood well, but by how hubs move. Not just networks. The whole structure of the network was controlled by hubs, which was moving with time, and it was a different structure between schizophrenics and controls, which again, it's something which is very much along the lines that many people have found since. So now let's go fast forward to today. After doing the work with the MFT with many cases, putting some connectivity analysis now back in Cyprus with EEG. And we are fortunate to have 3 projects, a local one from the local funding agency in Kratos, that I will say a few more things in a minute, a European one, ICON, that has 15 PhD students in the ITN kind of framework, in which Christodoulos is one of the students, and one for space research, European Space Agency. Apparently, each one demands a different approach. Here, what I want to emphasize is the commonality between the cases. The commonality, what I mean by that is that we can use exactly the same analysis to describe apparently very similar cases.
Andreas, you have 5 more minutes.
Thank you. So this is for the ICON project, which goes way beyond that. The Kratos project, it has the 2 main projects are astrophysics and neuroscience. And within neuroscience, we have 2 separate projects, one which looks at how we can look at children from their behavioral responses, accuracy, and the reaction time. We have a special device to actually do that and try to organize them and see how they are grouped together into groups. And what we found, again, it's a long story, which obviously will cover in 5 minutes. What you have found is that it's not only the accuracy and the response, but it's the path that they follow over successive tests. So we've done the test over 2 years, which actually can tell us the difference. So the analysis that we're going to do is going to be based on PCA, pairwise similarities. We're going to use spectral matrices, and you hear some talks, I think, in the rest of the meeting about that. I won't describe those in detail, but those can actually tell us, use the same methods to look at the responses for pupils, from sleep, and during sleep, from awake state. And very quickly, I'll go through just some pictures to show an example. So here, what we have the feature space, the multidimensional space reduced to a feature space and some clustering in 2 classes of people. Here, we use modularity part in order to identify clusters, and we can actually predict the way we use it. Here is using standard PCA. By using Gaussian PCA, we can actually do more. And here I have to acknowledge the work that we've done with Ioannis Michos and the Evangelos Papaeftimiou, who were actually continuing. And again, we can get a picture which is not too dissimilar, but it's not the same with the one before. And then what do? We can reduce into individual cases that we know. For example, this could be patients between 2 before and after intervention, as Panagopoulos would say tomorrow. And we can apply exactly the same results for awake state. And what I want to end with is this picture, which shows, so this and the next picture, which shows eyes open, close, fixate, an experiment that we established in Japan, and we used again here, in which we follow, not only can actually get the clusters, these are 50 trials for each one, 2 seconds to the spectral analysis and everything in the clustering over the space, but we can actually see how the transition takes place in the time between the 2. And not only that, we can actually go into sleep to exactly the same thing, do it there, and then look even at transitions, say here, between awake state with eyes closed and before. Okay, remind you, the last talk of the day, the second talk. And thanks to many people that contributed, but I want to start, show you a picture of Peter Fennick, the person that was in the talk, and the late Professor John Taylor, who was instrumental in actually establishing the mathematical framework, the validity of the mathematical framework for MFT. Thank you very much. I hope there's time for at least a couple of questions. Thank you.
Thank you very much, Andreas. You're perfectly on time. Let's see if there are questions. I see at least 2. I see 2 people raising hands.
Let's start with the first one.
One is Marios Antonakakis.
I know this guy.
Excellent. So let's ask him to unmute. You should be able. Yeah, excellent.
That was actually climbing, but anyways.
Good morning, Marios.
One question would be about the comparison that you did with normal controls subjects and schizophrenic, because you were talking about time varying hubs over there, right? Mm-hmm. So just a pure technical, how do you see, because you were talking about bivariate approaches. Have you ever tried to check all this stuff using multivariable approaches that take into account?
That's what they're aiming for. The reason why you could do that is because you have windows of about 15, 20 milliseconds across many trials. So and we look at delays, which would be mostly monosynaptic due to monosynaptic transmission. So using a time-delayed neutron information in short windows allows us to be almost certain that what we are looking is monosynaptic transition, therefore we can look at timing. In addition to that, we know the system. We know that, we see an activation which first goes to the amygdala, then V1. The 70 millisecond activation for V1 has a hub, if you like, in the amygdala, which is not it just tells you whether or not to continue or not. And you find that this hub is more active in schizophrenic patients. Basically, they cannot stop the activity, they continue, and the V1 works a lot more strongly than for control people, because they cannot really make sense of the stimulus because the amygdala doesn't let them. But anyway, I don't want to focus. That was just an example of what we could do. Thank you for the question. It gives us an example of what we could do using these techniques. You can actually look at the activity, and what we found is that it's not the propagation between one and the other. Now, let me say something which is more important, which comes to what we are doing right now. What we want to do, we want to take the network properties, because what we find is that the early information exchanges are very weak. We are able to do it because we have the localization accuracy, we can look at individual areas. But we have huge, absolutely huge responses later on, which cannot come from the monosynaptic transitions. Okay, it has to be for a network property, because we know that the feedback connections are much more numerous than the feed-forward connections. So for that, we need network analysis in a very serious way, a multivariate analysis. Thank you for the question.
I see. Okay, thank you very much.
Okay, are there other questions? Sarah.
Hi, thank you very much for this very nice talk. I agree with you that one of the main difficulties with subcortical is to have some data to prove that you are actually measuring subcortical and not some confounding effect. Do you have an intuition of which kind of experiment can...
Wait until Friday. Stay for the last talk.
Okay.
I'm not going to steal the thunder from Christodoulou. He's too kind for that.
Okay, so we wait. So
the question should be, do you need localization for that? Or just physics?
Okay, so it's exciting. Okay, so we wait until Friday.
We try to keep it exciting to the end, yes.
Yeah.
Okay, good. If there are no further questions,
I will ask a question, Alberto.
Oh, yes, please, Carsten. Go ahead.
Carsten.
If I can. Good morning, Andreas.
Sure.
Good morning.
Yeah. One slide you showed brainstem activation before eye movement. That was fMRI, or was it?
No. That was MEG.
It was MEG.
204 cerebral cortex.
So how many eye movements did you have to record for it?
We do localization for every single one of them, and this is the statistical analysis. That was our gold standard from brainstem. Peter Fennig wanted me to do the thalamus. I said no, thalamus. No, it's there. I need to have good models to describe it. Okay,
so it's
I understand your question.
Analysis, or
sorry,
it is not a single trial analysis where you see the
it's single time slice, single trial. Everything we do is single trial, single trial, single time slice analysis. Yes, and then we combine. We do all the statistics on top of that. We don't publish very often because it takes a lot. It used to take a lot of time. Nowadays with computing, it's much easier. But we need your techniques.
I mean, is it a certain kind of beam forming that you?
No. Beam forming is not tomography. It's tomography. It's a non-linear approach to the inverse problem. You use all the information from the single trials. It has to be non-linear in order to use the information from single trials. The only test that you can say that is not noise, you can look at you can compare the activations when you do the magnetic field tomography to the average signal, and when you average the vector that the MFT produces for every single trial, every time slice, and compare the two, and they agree, even at the level of the brainstem. So the reason, okay, the technical reason for that is because in the MEG, there is a component from the signal which comes from the primary carrier itself. And that is invariant, it's there all the time. But it's lost if you start averaging, if you start doing something, because it varies from time to time. You really need to go and do the problem non-linearly to get the very thin information that's available at that level in order to do it.
Thank you very much.
But unfortunately, the method is not open access. We want to make it open access, but we don't have the resources to do it.
Okay, thank you, Andreas. Thank you for your answer and for your presentation. Thank you again.